Hey everyone, and welcome to a demonstration of Per-vertex Ambient Occlusion in Unity, actually inside of Unity. This demonstration is going to contain some source code, which you can get from the project link in the comments below, and also shaders, which will be included in the same project. So for people who aren't familiar with the term, a definition of ambient occlusion, like I said here, it's a pretty literal definition. Basically, ambient means things that are all around, and occlusion means stuff that is blocking something, like an occlusion or an occluded orifice, which is a terrible thing to have. So if you look at this little screenshot down here, this is just some image I took from a site on Google Images. You see that basically areas where there is geometry that's sort of near other bits of geometry, like where the TV sits right on the wall, or in these little crevices formed by the doors and the gaps between the door and the frame of this TV stand, there's quite a bit of occlusion. We're just looking at ambient occlusion data here. There's no shadows or lights or anything. This is just what a surface looks like when it does an ambient occlusion sampling process at each point on the surface. You can see these what look like shadows sort of up against the wall where this roller hits against that and everything. And there's absolutely nothing occluding. You know, the ceiling, the floor, where there's nothing above it or around it, it's completely open, so that's an unoccluded sample. So that's what the effect does. So let's look at how we're going to do that in Unity. Let's look at it in Unity. So we have this kind of very basic scene. It's just a standard plane. You may notice this plane has been cloned, and I'll get to why that's necessary in a moment, but let's add an object, which will self-occlude as well as occlude the plane. So here you have this kind of complex, looks like a level out of rollaway. It's this little block thing. And this isn't like perfect geometry by any means. There's actually some gaps. You can see this edge is sort of almost self-intersecting, and there's reasons for that. I'll get into those in a minute. And it's lit by a single light, which has a little bit of kind of well, it looks more like a Band-Aid. It was supposed to be sunlight. I don't know. It looks a little bit like a Band-Aid. But, and I'm doing that intentionally, just going to leave some very boring lighting on the scene. So let's click on the object and run our AO script. I'm just going to run this with the default settings. And let's take a little while. This is actually performing, you can see up here, 512 samples per vertex, and there's quite a few vertices in this object. So it's going to take a little while. This implementation is not suitable for real-time use, but I'll get into how you can sort of change it later. All right, so nothing changed at all. Why is that? Well, because we're using a default shader, and we need to use a shader that actually shows us ambient occlusion data. I'm going to use one that is a debug shader that just shows ambient occlusion data. So click that on here, and actually I want to undo these changes so it's as default as it can be. Gosh, that's ugly. But it's a good indication. This is what the effect is really supposed to look like. And if you've ever seen a per pixel rendering of ambient occlusion, it is quite, this blotchiness is sort of inherent into the way the algorithm works. So, all right, let's use a somewhat more realistic shader where it's actually, this isn't considering lighting information at all. This is just the ambient occlusion data is actually being baked into Vertex Alpha. This is visualizing that across Vertex RGB, but that's all it's visualizing. It's not taking any other information into consideration. Let's use one that takes the scene illumination into consideration. It looks much better. It's this nice kind of subtle effect. Let's make it a little bit less subtle. Let's kind of blow it back out, and let's actually make the color black again, so it's as hideous as it was before. Okay, quite a lot of data. Now, looking at some benefits. Well, here's we're generating ambient occlusion. Okay, we have it on our object. We feel pretty good about that. We have these sliders, one over here on the left. Actually, let's do it this way. Let's just change, so look down and see this area in here where it's quite a chunky effect. If we change sort of the exponent that this effect is being raised to, effectively kind of clamping the effect, we really sort of want to drive it into the corners, can clean it up a little bit. So we can do that to affect this. We can also reduce its intensity by quite a lot to the point where you can't see it at all, make it quite a bit more subtle. So let's just clamp it in a little bit and make it a little bit more subtle. All right. And before I demonstrate some of the reasons why I like this, I want to talk a little bit about why you might use it. Go back to our slides over here. So what is the purpose of generating an ambient occlusion pass? Well, one thing is that it's subtle shadowing, and it adds surface detail and helps pop edges out. And I want to show that very clearly in a minute with an A/B comparison inside of Unity. This can help break uniform surfaces up, add visual complexity, and it can also help glue separate objects together. So if you have an object that's supposed to be sitting on one, and even if you are using shadows, shadows in Unity are always going to be completely directional, and in the real world, things are never really quite that simple. There's always a little bit of bleeding or color blending at the base where two things are really joined. So we want to capture that as much as possible, and ambient occlusion helps us do that. So let me demonstrate those effects right away. So here we are, we're in this scene, and we don't have very sophisticated lighting in the scene now. If we look back here, I'm just going to get the camera like this. All of this surface detail, you can see, you're looking at where these vertices line up and where the edges break and stuff. There's actually quite a bit of geometric complexity here, but it doesn't look like it. Everything's just one color. It's this kind of horrible, muckledy brown, nasty color floating here. And there's no, as you move the camera around, you see some things break up, but for large sections of rotation, it's very difficult to tell what you're actually looking at. Now, this is an extreme case. There's no texture data. There's only one light source and all that. But you often end up with something like this in real-time games where it's just kind of this haze. It's just this soup, and there's really no way of breaking it. If we go ahead and put our ambient occlusion data back on here, there's really nowhere where it looks that flat. Everything's broken. I want to show this edge in particular. Watch like this edge right here and this corner down here. As I put the standard shader back on, they just disappear. AB, AB. You can see how much geometric detail just pops right back out into the scene when we don't have a standard non-AO object here. And this is very difficult to accurately capture all this information in texture data. I mean, of course, artists always paint these sort of textural details in. That's one of the reasons why even this flat object is cheating a lot to demonstrate the intensity of the effect. But even with such a flat object, just a single ambient occlusion shader may not be the most beautiful thing in the world. A little bit smudgy up in here. It looks a little bit like it was kind of drawn in with charcoal. But it's really not that bad in effect, honestly. And you can see sort of where that would help a scene look quite good. Let's add a slightly more realistic lighting. So one thing that, this is all being done for a game project we're working on. It's sort of a gigantic open world MMO. One thing that we're using for more realistic lighting is an old trick from like, believe it or not, there was a time GI renders weren't fast at all and were really shaky from one frame to the next. So people didn't use them in animation. One thing that they did to simulate like that sky dome, diffuse, even lighting on everything is a whole bunch of dome lights. Let's turn some on. And you can just see there's this little wedding cake over here of dome lights. These are all actually in Unity being run as per-vertex or spherical harmonics lights, so they only cost one pass. This isn't like some crazy deferred rendering only scheme, and it's not going to cost you, 14 render passes in forward. They're all vertex, so they all get included in one render pass. And here's where that sunlight color starts to look a little bit more like sunlight on one side and a little bit more like the blue sky reflecting off of the far side of the horizon on the other. And here, the ambient occlusion effect looks really quite good. Now, talking a little about gluing objects together, well, other than the fact that the normals here aren't bent at all, so like there's no attempt to have the normals between this object and the ground object sort of blend together and meet. So we're going to get very even sort of bluish lighting on this and very yellowish lighting primarily from this sunlight up here. So that's not going to ever really look particularly good. You have to handle that separately. But ambient occlusion can help. So we're going to go over here, bake A over data. I'm going to actually use I was using a range of only 1.5 meters for the other one. I'm going to use a larger range of like 8 meters this time. Go ahead and run that. And you'll see it pops this. Now this has very coarse geometry. There's not that many vertices, so it's a very coarse effect. And ambient occlusion, anything that's vertex color based is going to basically be interpolated from one vertex to the next. So the direction of edges is going to affect the direction of that interpolation. So you can see this, what looks like a directional blur having been applied to the shadow. But even so, especially now, actually here, I'm going to use a vertex only version of the shader. It's worth pointing out, here's one thing to point out real quick. This effect is being calculated per vertex and can be displayed in the shader either per vertex or per pixel. You can do either vertex interpolation or pixel interpolation, depending on whether you want it to be in a vertex or fragment shader. There are differences between the two, which aren't really worth demonstrating here, except to just point out that this project includes both, and you should think about which one you want to use. You also should think about creating separate materials for each object that needs this effect applied, and the reason for that is this intensity and power setting are probably going to be different. Like, so for this self-occluding, smaller, more finely detailed object versus this ground plane, the settings for the material aren't going to be the same. So you still want to have per object material control. You can't just use like one shader for everything. You couldn't do that anyway because obviously you'd have probably textural problems, but it does make it more difficult to use with texture atlasing. Just something to keep in mind. All right, so we're going to go down here. We're just going to clean this up a little bit, clamp it, and bring this down, and okay, let me use the right one. Clamp it a little, bring the intensity down a little, and that's nice. And that really does provide a little bit more information to sort of root that in it. Now, this is a scene with no shadows, so let's turn some shadows on. I'll actually use soft shadows for maximum beauty. And you can see where, okay, these soft shadows look pretty good. We go back to the standard, and we can see that, okay, with the standard material, the soft shadows look great, the occlusion up here looks great, but it looks even better, even with the kind of sloppy pixel shading version, the sloppy vertex shading version. This looks pretty good, and we can also lower that intensity so it's just peeking through. Really helps sit this object on top of that, because you need that occlusion, you need that sense of there being an object really resting on there in the light, which without this, even though it's actually not quite resting on it, I guess because I moved it down. There you go. You can also see, by the way, down here, these occluded, very heavily occluded foot of this thing as it's sitting right on top of the surface. All right. So this is an interesting object, but let's look at some variations on this. Oh, okay, one thing I actually wanted to demonstrate, talking about why this thing was a clone. So here we have this object, and here I'm going to actually turn this up so it's as visible as possible. What happens when we save this scene? This object, by the way, as you can see down here, is imported. This is an FBX import, FBX importer. And this is probably how you would start, you know, doing your scene. You have your little FBX importer, and you drag this out, and you, oh, this is great. And I run my ambient occlusion, and then I save my scene. Oh, and all my ambient occlusion disappears instantly. And the reason that happened is because the mesh that actually comes in with your imported geometry, in this case, includes UV and color data, and it almost always will, from Modo or Studio Max or Maya. And you probably want it to, because you want to be using these channels as much as possible, especially vertex colors. They're very powerful, they're very useful in a lot of different cases. So in order to keep it from overwriting that, we have to go over here to Deep Copy. And you'll notice we have this clone object. Now this is just a script that's also included in the project. And basically it breaks the relationship with that mesh. So now we have this object, and I'm just going to use a very small number of samples. It'll look terrible, but this is just to demonstrate very quickly that with a smaller number of samples, and that's why it uses 512 by default. This is what it looks like with 32, but I save, and there it saves. It's no problem. So, all right, we have that. I'm going to take a very low resolution mesh first. This one you can see right away has far fewer vertices. You can see these edges, you know, not really a lot of data on here at all. So we're going to, again, bake our ambient occlusion data. Again, nothing changes. We're going to apply our shader that actually uses that data and, you know, tweak this a little bit so it's more beautiful. And it does look quite nice, doesn't it? It's sort of feathery in there. And you'll notice that we have some artifacts, though. I'm going to turn this back all the way out, put this all the way out. This whole area shows up black, and that's because every one of these points is actually quite heavily occluded. There's just not enough information to pick up that this area in the middle is not occluded. So, but even so, even with not quite enough information to do this very well, reduce this back down, it still looks quite nice. I mean, like that, if you can imagine this being like a really low poly asset, like on an iPhone game, or just like a background thing, even level of detail, anything like that, it doesn't look bad, even it's quite inaccurate. You know, I have these big triangular shape here, and there's no corresponding triangular shadow here, you know. Oh, these are real shadows, and maybe I should turn that off for purposes of illustration. Yeah, so you can see like this corner just didn't really come out quite right at all, but even at that, it's still not a terrible effect. This edge in particular looks quite good. This whole thing just looks better than it would. Just like that. That looks like VRML, looks terrible. This looks quite believable. That's very nice. So, all right, go turn our light back on. Getting there. All right, so we're going to hide this object. Oh, and again, I didn't bother deep copying this, so of course, as soon as I save, that will all go away. See if I can remember to do it next time. High resolution mesh. These meshes, I know these are terrible meshes, and I also know that the light's blowing out. That's okay. I just put a bunch of bloom on there. It looks great. So let's go ahead and deep copy and delete the original. Take our deep copy, slap on our pixel shaders so we know we're going to get the effect right away. This one will take a little while to run, and one thing I'm going to do is I'm going to jack the number of samples, oh sorry, the distance rather, and I'm going to have it average colors. And this is to demonstrate, actually probably not a good advertising tactic, but I want to demonstrate a pretty massive failure of this system. Something that doesn't look quite the way it should. And then jack this thing back up to full strength. Go over here. And actually, you know what? I'm just going to go ahead and show the straight debug shader. And you can see in here where this is some normal data funkiness. Just terrible, really. Seams, big jagged edges, stuff not really interpolating quite well. And this is with average colors. It looks even worse without. You know, well, you get things like that. You got them using proper 2D anti-aliasing, I'm sorry, you know, bitmap anti-aliasing as well as a render pass. Still looks pretty good, and with actual texture data and stuff, it should look okay, but, you know, you can definitely run into some issues here. If you run into too many of these, you can fix them by hand. There's an outstanding plugin for Unity called Vertex Painter, which is very cheap on the Unity Asset Store, and you can just paint some of these edges away by hand. I mean, it's lame, but you can do that. You can also, you know, tweak it so that it's a lot less visible once you adjust the intensity effect. I'll put this back on the pixel shader. Again, make some tweaks to intensity. Actually, I'm going to leave the effect as a full intensity for the moment because I want to highlight another feature of the shader in particular, which is that you can change the color of the ambient occlusion. So we put it on full red, just sort of highlight, you know, how bad really full straight black actually looks here. It's creating some, you know, we have this nice sort of sunlight color, this nice sort of ambient occlusion, ambient sky color, sky dome, this blues, and we're getting a lot of like this gray sort of mud here in the middle. We don't really want that. That would happen on a lot of surfaces. So what we do instead is we pick kind of a sky-ish color and actually do a little A-B here where you can see this without the sky color, with the sky color, without the sky, with the sky. It's quite nice with the sky color. It's especially nice with the sky color if you also, again, sort of damp the effect down a little bit so it's not quite so overpowering. And then even on this kind of, you know, beauty pass where you have full soft shadows and it's light and, you know, all the scene lighting coming in from these GI lights, put the standard material back on here, so much information, so much complexity just drops completely out of the scene. Even on a very complicated mesh with very good lighting, it just goes away. So we really like this effect. And okay, so that's pretty much a demonstration of the effect. Go back to sort of discussing the merits of this. So we saw the subtle shadowing. We saw how we add that complexity. Again, going back to the... actually, I want to use the medium res one for this. Going back around the back of this object, you know, even with all this lighting information, all these lights and all this nice shadows and stuff being cast with a normal shader, ugh, you know, so much. I move this camera up here in particular. All this is all one block. Doesn't look very good at all. I'm actually just going to calculate this again with proper settings, so we're not looking at the ugly 32 sample version of it. Yeah. All right. You know, quite nice. Really does just pop that right out. Even at very unimposing settings, you can still, you know, A-B. So much detail coming back in there. So that's this point, right? Adds visual interest. Then helping to glue separate objects together. Look at that. Very subtle. But if you look here at the ground, right in here, move, you know, A-B. Really does help root that object on the plane there, even with, you know, again, crap, low, horrible geometry. All right. So what are some of the advantages of doing it this way at Per-vertex? The first big advantage is it's very efficient. You're paying to store this stuff anyway. It's all gigantic array in memory. Every mesh has, you know, tangents, normals, UV data, the actual vertex locations, and then also this color array. Now, in Unity in particular, these aren't really always populated. And in fact, in the web player in particular, I think it's all stripped out. With any compression applied, it's all stripped out. So you'd actually have to go through some gymnastics to preserve some of this information. But it's worth it because you are basically paying the overhead, and especially for any complex asset, you're always paying this overhead. This only uses one vertex color channel. It can be any of them, RGBA. I'm using alpha in the scripts, but it's easy to change that to whatever you want. So the first thing is that, you know, you're getting this basically for free on top of something you're already using. The other thing is it's very low cost. Compared to, say, like a render pass of ambient occlusion that was actually high enough resolution to be useful, this is quite a lot smaller. It's only one sample per vertex, and it's only one channel, so it's very low footprint, small footprint. Easy setup. Again, this is really the big one for me. You don't need any UV data, and it's actually, look at it this way, it doesn't require UV data, but if you do have UV data, like for instance, if there's, you know, symmetry or lots of sharing of UV data between faces and vertices like you'd have on a house or a character where, you know, the left and right arms are mapped the same way and everything's sort of symmetrical, sharing UV space. If you were to paint shadows into that environment, they would have to repeat everywhere that they occur. Well, you know, basically it would be like texture data. It's going to repeat with the texture data, which might not necessarily look quite right in the physical world where, you know, texture is repeating, but the occluding object that was there on one part is not there on another. So you have this random shadow floating in space. Well, this doesn't require or even consider UV information, so it's always going to allow unique features to be displayed anywhere there's vertex data to store it. So, and it's I mean, you just point and click and you're done. Like, that's it. That's the easiest thing in the world. An easy process. That's the next point. One-click hooray. I mean, that's really it. You don't have to do anything. It is possible, technically, to transfer a 2D normal ambient occlusion pass from Mental Ray, and especially from Modo. Modo lets you do this quite well with their image ink. Basically, you render ambient occlusion out to a pass, use that as image ink, and then paint vertex colors in one shot using that image ink. But that requires UV information, so it suffers from all the problems that UV-based painting this into the actual texture data would. Not to mention, it's a pain. It's hard. It's a long, slow process. It's not clicking once and being done. And the other thing is that it's very fast. It's really just, there's a simple one lookup and a multiplication to add this to any shader at all. I mean, the shaders that this project comes with are very useful, but you can build this into anything. And there's really virtually no cost for running them. And you can do a real-time version of this, and I'll get into how you would actually do that. I want to take a little bit of a look at how this thing works here for a second, and then we'll look at how you would make this real-time. So I have this little point. Here's this little blue sphere down here. And the way this thing works is in the script that's actually handling the ambient occlusion process, it looks to see if the sphere is active in the scene, and if it is, it tests every vertex against its position. So when it finds that this sphere is on top of a vertex, it then compares the normal at that vertex with the z-axis of this sphere. If they're aligned close enough, it's going to do a sample test. It's going to basically a debug sphere showing us what was actually sampled at that location. So let's run the GI on this thing again, and I'm going to do the expensive one because it makes a more clear dome. Let this complete. So taking this time. All right, great. And now we have this dome, this hemisphere, demonstrating how the ambient occlusion process works. So basically from this point, ignore this brain-looking blue lump here for a moment. It's useful, but at the center of that is the vertex that all these rays were emanating from. Remember, it's taking 512 ray samples per vertex in the mesh. So this is one of the hemispheres that are generated as part of the test. And you can see that everywhere there's a green sphere is where a ray was cast and didn't occlude anything in a certain distance. There's always a max radius that's considered by ambient occlusion. All these green spheres is where nothing was hit. All these red spheres are where something was hit. And you can actually see, like quite well, yes, it would have, as it cast out here, hit the edge of this part of the object. Obviously over here there's nothing. If it were casting below, it would hit everything, which is why we don't do a cast below. It's why it's a hemisphere. And you can see, I'm just going to hide this for a second. You can actually see what that sphere looked like, what the dome of samples looked like. You can also see a little bit, it's not quite uniform in distribution. Like there's nothing going straight out, for instance. So an object sitting up here, like a pretty decent sized sphere, actually could fit directly above the surface and wouldn't contribute anything to occlusion because no ray hit it. You can get around that a number of different ways, but it's something to keep in mind, that you might need to think fairly carefully about your sample directions. The one thing I want to point out, these little blue domes, what's sort of useful about them, the way the script works, if you actually just cast a ray, a sample, from the vertex location itself, it's not necessarily always going to do anything useful. And to demonstrate that, look at this vertex right here. Imagine if this setup had been run on this vertex here instead, right at this corner. If you don't do any offset, if you just cast the ray directly from that vertex location, one thing that's going to happen is it will never occlude with this wall. Like this vertex down here will never see any shading really from this object. And the reason that's true is because this is using physics line cast under the hood. And for line cast to report an occlusion, or collision, something has to go, a ray has to be not inside an object and then go into the object. It's actually traverse the object boundary. Since this point is on the object boundary, it can never traverse the object boundary. It's always on it. If it goes out this way, it never crosses it. If it goes out this way, it never crosses it. If it goes nowhere, it never crosses it because it's on the boundary to begin with. So what this thing actually does is, let's say that, that's the location we're starting at. We're going to go to this point up here. What it actually does is it considers a vector from here to the origin, and then that bounces, almost like bouncing off of a mirror. It's going to move away in the direction of the normal, but away from the sample location by a very tiny amount. And then from there, move out to the sample location. And what that does is it allows you, it kind of moves you away from the wall and then into the wall as it considers the sample out this way. And that's partly how this gets such a smooth effect near walls, which is otherwise very difficult to achieve. Even though it's not all that pretty, believe me, it can look a lot worse if you don't have little bounces like that in there. But anyway, so for real-time performance, okay, this is drawing quite a large number of samples. So one thing you could do for real-time performance is just have fewer vertices, A, and far fewer samples, B, but we saw that that doesn't really look very good. So like if we kill these points, hide this guy so we don't get the sample sphere drawn again, hide this, and take our much lower resolution object, and do this sample, and this time we're only going to use 16 samples. First and foremost, it's not going to be quite real time. It's very fast, but it's not real time. And secondly, well, actually, on this mesh, I don't know, that doesn't look that bad. Yeah, don't listen to me. Totally do that in real time, kids. It's great. I don't know. I'm not really seeing too many problems with that. That might be great. Oh yeah, that might be one thing you could do to get a real time effect. The other thing you can do though is for some types of real time occlusion, you don't really need. This is using a mesh collider as the source for all the collision. You probably don't really need that. What you can do for some things, like I remember when Unity recently announced their Flash Player version again in October, they had like this game Shadowrun, I think Big Point, Shadowgun. Shadowrun was an old Genesis game. Shadowgun, and underneath the character, there's this semi-densely tessellated plane that follows the character around. And each point on the plane is going to be receiving some amount of occlusion data, which will come in the form of a sphere. There's going to be a sphere basically in each foot in the player as they're running, and a sphere in the midsection of the player. And so this shadow is going to get sort of real-time ambient occlusion, or look like it's getting real-time ambient occlusion from the player's geometry. And because they're using spheres, all they really need to do is at every point on the surface, they just evaluate the distance from that point to the sphere and set the occlusion based on some heuristic or some rule based on that distance. And you don't need any samples. You don't have to sample, a million different directions. You're not looking for geometry. You're just measuring a distance to a known object, which, because it's a sphere, only requires a distance check. It's just one position check, and that's it. So things like that can be extremely efficient for faking AO. In that case, the shader gets a little more involved. You'd probably have already full black vertex colors or a full black effect. And all you'd really be doing would be controlling the alpha. So you would need full alpha blending for that. But it's still really, really simple. And you can definitely do good real-time fake AO. Also, this isn't like the cheapest mesh. What does this thing have? Yeah, I mean, this is still 617 verts at 16 samples. It looked like that actually might be very fast. I have to do a test with that at actual real-time and see if this works in real-time rates. But it might. So there you go. That was it. That's the presentation on ambient occlusion inside Unity. You will need, to make it work, you need this deep copy script so you can make sure that you break the reference to an imported mesh so that the ambient occlusion data you actually store stays. And the actual bake script, there's some properties that, we can go through properties maybe in another detailed video. We can just look at the comments in the code because they're actually pretty self-explanatory. Just play around with them, works. Works very well in extremely simply lit games, works very well in games with more complex lighting. I haven't really done anything with light maps. We're just not going to use them for what we're doing. But looks quite good and does what it promises, Really adds that visual interest, adds that glue, and is cheap and easy and fast and all these great things. So, thanks, and I hope you enjoy it.